So there's our first lab. Determination of potassium hydrogen phthalate. So potassium, chemical symbol K, so we call it KHP. So for the hydrogen phthalate, HP, so KHP. And the weird thing is phthalic acid is diprotic. So it should be a 2-to-1 acid-base reaction, but we're not using that acid. So the first reaction is the prep that the chemical companies do to make KHP. So there's our starting reagent. And we see we've removed one of the acidic protons and replaced it with potassium, and then they can crystallize that. This is a weird compound, right? So why the heck are we fussing with this diprotic acid in a monoprotic form? The reason is we can make this to great purity. It's known how to make it to 99.49s. Where's my 4? 4 nines. Yeah. 4 nines pure. So that's called a primary standard. So KHP is a primary standard. We can get it really pure. Now, when we do acid-base reactions, the base we'll use, that's down in the next, is sodium hydroxide. Sodium hydroxide, I don't care how rich you are, you can't get that in a high purity. Okay, so we'll have a high purity starting reagent. We'll use that boiled water to make our base, and then we'll do a titration for the monoprotic KHP. So 1-to-1 reaction. We'll dissolve this. This is a fine crystal substance. It's a little staticky. That is, it builds up a surface charge, so it can be a little tricky to weigh out. And there's some crappy YouTubes doing this experiment. I actually had one queued up and I watched it yesterday and went, they made so many mistakes in their procedure, I don't want to show it. Okay, but you can look at it to see the color of the endpoint or something. But so it's a simple 1-to-1 acid to base reaction. So I just call this, it's KHP, but I like to call it HA. A is the organic acid. I hate organic chemistry. I do elemental analysis, so the A stands for the organic part of this molecule. The H is the acidic proton that I care about. So when I show it to organic chemists, I say Ha. Okay, so Ha reacts with sodium hydroxide, and we end up neutralizing that sodium hydroxide. So very simple, and the results are water and a salt. Okay, so if you do the titration exactly to the end point, also known as the equivalence point, actually, since it's theoretical, then we should have just salt water and water. So salt water. So when I first moved to Idaho, I had a student take I guess it was my second year, a student said, oh, we did this titration in Twin Falls, at Twin Falls High School, and the professor lets us drink it after we're done. And if it tastes sour, we know it's still acidic. And if it tastes slippery, then we know it's still basic. And it's true, but we won't do that. We'll use and they used a color indicator. And yeah, back in the day, that was something people would do. But please don't, why did I even mention? Don't drink your chemical experiments. That's safety rule number 1. All right, so then if we're not drinking it, how are we gonna know when we get to the equivalence point? So that's in every titration, we have an equivalence point and an end point. Equivalence point is when we have a 1-to-1 ratio of reactant HA and OH minus, okay? So that's the theoretical, stoichiometrical equivalence point. We're not gonna be able to detect that. What we're gonna detect is the endpoint, a visual endpoint. And so I've added some notes, and you might take these notes. So to monitor the reaction, we'll use phenolphthalein. Phenolphthalein is a real common acid-base indicator. So I did some great research on Wikipedia, and yeah, you're welcome. So initially, when we start the titration down in the, and I'll do a little drawing in just a second, down in the Erlenmeyer flask, we've got HA, so we've got an acid solution, and phenolphthalein is a nice indicator for high accuracy because it goes from colorless to colored. And so as soon as we start to see any color, we know we've passed the equivalence point and are now at the end point. So the end point is when we have a visual indication. So if we make it light pink, then we only went a little ways past the equivalence point. And that's probably a good point to stop. Well, you think it would be better if I could just see that equivalence point, but there's no way to see it. And we're going to do a standardization and an analysis. We're going to do 2 steps, and each one will require an endpoint. Since the endpoint is likely the same, or you'll try to have it be the same on both of them, that endpoint equivalence point error is canceled. See, we thought this crap out. We didn't just pull some experiment off the Gen Chem table. So we're going to have to do 2 titrations. The first titration, remember that KHP, we can get a primary standard. But the sodium hydroxide, no such luck. So we'll do 2 titrations. 1 to standardize the sodium hydroxide, 1 to analyze the unknown. Same reaction where KHP reacts with base. So it's weird we're going to do 2. So I like to draw pictures. So let me draw a picture of that. So the KHP. Trying to get this all lined up. I've got monitors on down here too to watch. So So the first step is to standardize a sodium hydroxide solution, and we're going to use standard KHP reagent. And I'll diagram that in a second. And then the second step is our final step. We're going to analyze the KHP, that's an N. U-N-K, unknown, using the same sodium hydroxide solution. So in both experiments, let's do it step 1. I like cartoons. Step 1, I'll start with a Erlenmeyer flask. Okay, and in it, I'll add standard KHP. And then we'll weigh that KHP. So we'll know, we know the formula weight, it was just there on the formula weight's 204.22. Whoa, show it for you. So if I know the weight, I know how many moles of KHP are in there. Then up here, I'll have my sodium hydroxide and a burette. Right? Boop, 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 boop. Now, I don't know the molarity of the sodium hydroxide, so that's what I'm doing in step 1. So sodium hydroxide here. And now at first the KHP is solid. We'll add some water. We use stir plates. That sound effect is the stir plate, in case you didn't recognize it. All right. All right. And then, as I like to say on Friday afternoon club, we'll drop the bass. Drop the bass. Okay. Drop the bass. So we'll have sodium hydroxide, and we'll know how many moles of KHP are here, and then we'll see how many milliliters we use to come to the end point, and we'll use that difference to calculate the molarity of the sodium hydroxide. Okay, step 2 looks the same, so it's a little confusing. I got to move my camera. Step 2, same sodium hydroxide. But using the information from step 1, we know its molarity. So we'll say sodium hydroxide. Now we say that's 0.9976 molar. So whatever we calculate from the first step. And we'll drop that into a solution of our unknown. So now we're going to put unknown KHP. You can see how dyslexic I am when I start words in the middle. The same titration. We go from colorless, so clear, to pink. Okay, and everybody, not everybody knows, but a lot of people know, we just go to light pink. Okay, because we want to match it. So this titration, we go colorless to light pink. A similar endpoint will give us perfect results. Okay, so we want to, if we go to dark pink, then it changes all the indicator. And you could go 2 drops over and it's dark pink, or you could go 40 drops over and it's still dark pink. If you go to light pink, you'll go half a drop further and it will be darker pink, right? So that's why we'll try to just get the first little bit of that indicator to shift from colorless to colored. And it's easy. Now, if this was red and this was pink, then we get an intermediate color where both of them are present, and it interferes with our endpoint. But because we go from colorless to pink, it's a very clear, very easy endpoint. And I've had, you're like, oh, how many people really in lab do titrations? I think I've had 37 master's students, and I bet 27 of them have done titration somewhere in their research, because we don't have an instrument that could do the same steps. Okay, and you can, if you want, you can try to film. I always say, take a picture before you start, click of the start of the titration, and then down to here, take a picture of that color. And then down here, when you're done, take a picture of that endpoint. Now you have a video, not a video, a graphical representation of that titration. And you run all your numbers, they all look the same. You think you're probably good to go. But if one of them sticks out, then you can go back and review it in time. And it's kind of handy. Okay. So that's the KHP lab. So usually we do 3 trials. 3 reps and 3 reps. Okay, some people, it's your experiment. You can do 1 rep and 10 reps, or you could do 2 reps. but they're equally important. So the first day, we definitely want to finish at least 3 reps on step 1. That leaves the whole second day to do 3 reps of 2. A common thing that happens is people will run 3 or 4 reps, because sometimes we just blow it, right? It turns dark pink. Don't even write it down. Just start over. No harm in that. That you don't ski well and not fall down. You know, if you're going for it, you make the big wipeout. Well, if you're going for it in Quant Lab, you get a Christmas ornament down here instead of a light pink. But you try to get three good reps, and then the first day maybe get one or two unknowns run, and then the second day you get 3 and 3. Good for you. Not everybody's going to get that far in 3 hours, but let's hope we do. And then the next day, maybe do 1 of these, then 1 of those, 2 more of these, and 1 of those, and then quit. But don't be overly systematic. So when we're working in the lab, a lot of our errors come from our progression. If we always do the standardization first, we're not warmed up. We're not as good at what we're doing. So it's good to do a couple of the unknowns and do a couple of the standardizations, and then you work up the data all at once. Don't even bother. You only have 3 hours, so get as much lab work done as you can, and then somewhere else work up the numbers. That usually works best. Try to avoid regiments. People think, oh, I'm getting good at this lab, I'm going to do this. If you do it the same every time, you make the same mistake every time. You do things different, do 2 titrations, take a break, go in the bathroom and cry, or whatever the hell you got to do. That's what I'll be doing. All right. And then come back and do 1 of these and 1 of the standardizations. Just try to mix it up on purpose. You got to pay attention, but it's okay to take breaks or change the order of things. So one thing that students have found in this experiment is you shouldn't start it. The book, the literature says it's okay to start before all the KHP dissolves, because as you titrate away some of it, the equilibrium will shift quicker into solution. But if you're cranking on that, you might get ahead of equilibrium. So we got to really go slow. The idea is once you do 1, now you know where the endpoint is. Jam in a bunch of titrant, then go slow from there, drop by drop by drop. Okay. And in fact, let's go back to the picture. In fact, we're going to try, you think, oh, 1 drop, that you've seen that in like Gen Chem or somewhere else, where 1 drop is the difference between clear and colored in your titration. That's right. So pat yourself on the back and then do it better. So to do better, I'm going to blow this up. I got to get a fresh sheet of paper. So here's a bigger burette and a stopcock. And people have different ways to do a little bit of, hey, it's crooked. All right. So the stopcock lets the solution out. Some people like to do additions by spinning it. Others like to turn it just a little and let a drop build up. So let's look at that situation. So a free falling drop is going to be about the same size every time. So if I set it to drip, the volume once it free falls is about the same over and over. But I could slow it down a little more, or even in this case, the drop first builds up down here, right? So before it gets so big that it falls, then you can shut it off. And now you have a hanging drop. And more precisely, a hanging fraction of a drop. Okay, well, sometimes you go, well, that stinks. No, just grab your wash bottle and rinse it in. So we'll have lots of good deionized water that doesn't have a lot of acid in it. And you can just rinse that half a drop into your solution. So down here's your, and see what it does. Maybe a half a drop will turn it pink. Or we want it to stay pink for, gosh, for X seconds. I can't remember X. I think it's 15 seconds, but I'm not sure. So it has to persist with stirring. You know, right when it hits, it's pink, even at the start, because there's a high concentration there. Once the stir bar gets going and it gets mixed in. So stay for X seconds in a homogeneous for the whole solution, the entire solution. Because people go, well, I'll save this one and use it for a comparison. But if it's a really light pink, the CO2 and air comes in and it changes it back to clear. So they'll let, it depends on your like I like it to make it fairly clear that it's pink. I go a little heavier pink, but I do that in the standardization and in the analysis of the unknown, and then they cancel out. Some people like to go, I'm like, is that pink? And they're like, yeah, I can see it. I'm like, are you sure that's not reflecting off of the pink flowers down the street? It's so faint pink, you know, and that's fine. That's great too. That means your titration air and your endpoint are very similar, but can you reproduce that? So there's a personal preference there. Okay, first thing we got to do, I said I'll quit at 45 after, so I got 20 minutes. So I want to talk about washing dishes. So contaminants from previous use of glassware can interfere, but also soap is one of the worst things. You can contaminate these things. Now, our first lab, soap's not a bad contaminant because the soaps we use are usually pH neutral. So soap's not so bad. But once we start doing nickel and calcium, then we're going to have metals. And soaps are designed to react with metals. Soaps are called anionic surfactants. So too much soap, don't get crazy with the soap, and make sure you use the right kind of soap. So I'm going to give you, I know you're dying with this. One, we're going to wash dishes. One, cold tap water. Okay, that's my preference. You got it. So I call it cold. So just turn on the cold tap. Hot water tends to have more contaminants. It dissolves the pipes, that sort of thing. So that's why, and it sits in a water heater. So that's why I use cold tap water. Sometimes you'll find, like some students rather have it hot for washing and then cold for rinsing. Okay, potato patata. But you start to see when I worry about the temperature of the tap water, you're starting to see how much I'm concerned with what contaminants are going in there. That's why wearing a lab coat is usually a good idea. Gloves are always a good idea, and this year they're required. So, because your dirty little grimy hands, I mean, you don't have ex-president hands. You have, but everybody's hands are dirty and grimy. All right. Cold tap water and very soluble soap. So there's usually at least 2 soaps in the lab, and one is powder, and we're going to use the liquid. So if the soap's not highly soluble, then it won't rinse off as well. If you use a solid soap, they have to dissolve first. So that slows down the rinsing. So we have a liquid Alkanox. It's a soap that I talked the stockroom into buying years ago, and now they use it all over the building. But there's still these solid soaps. Don't use the solid soaps. They're too slow to and then 3, if needed, use a brush. So there's the burettes have a special brush for cleaning. They're the ones that usually need brushing. The burettes really need to be cleaned. The Erlenmeyer flasks you're going to use are washed so many times that they're usually clean to start with and clean to finish with. And then 4, rinse with tap. And this time definitely cold tap water. And then you finish it with, I rinse with DI. So the deionized water taps have an automatic shut off. You want to let them flow for, you know, we're not the first lab, we're the second section. So the other lab should kind of get the DI taps going, but we let them flow 60 seconds at the start of each lab. So we get rid of dissolved gases in the system and we get good clean DI. We're not done yet, you know. So we'll look at sheeting action and hold up. So is the thing clean? If my flask has a, I'll dump it, it'll probably be upside down, but you'll see like a whole front. So it will be either wet or dry, and that wetness will move towards gravity. Or you'll get, that's clean. So a sheet, I love when the Nepalese kids say sheet. The sheet, I sheet my pants. No, the sheet is clean. Drops are bad. And my spelling's bad. So if it's covered with droplets, so look for sheeting action. If it's clean, you're done. 7. So I didn't misspell it. If and only if, IFF, if and only if droplets persist. And there'll always be a few droplets, but you'll see these ones that hang on the borosilicate glass. It shouldn't attract a polar solvent like water. So if the droplets stick, then rinse with 6 molar acid and repeat. 1 through 6. Okay, so Friday's probably the most likely day you'll have to hit stuff with wash acid. So usually hopefully they'll have wash acid out. Stockroom's struggling with they're not allowed to have all these student helpers because of COVID. So they're working really hard to be ready for us. And hopefully they'll have some 6 molar hydrochloric or nitric wash. That acid will pour into the flask, let it swirl it around, let it sit a few minutes, and then pour it back in the wash container. So we don't put the wash acid's going to be a little bit dirty, but it's okay because we re-clean. Okay. So questions? Can you believe you're in a 200 level class learning how to wash dishes? I know it. But this will help you out. You'll appreciate that. Okay, that is not in the intro for the lab background material. It's listed. The balances and the, I got to keep going because I made you a promise. So the other things we want to talk about is, I think I'll start a new page. Balances and titrations. You can look at the intro to lab techniques. What is it called? Yeah. Oh, info dot 4. I think that would help you. And you might look in your textbook. Do you have a textbook? I don't know if you have a textbook. Is there a textbook? No, but anybody will still awake? If there's a textbook, you can look it up. Look up titration techniques, stuff like that. And there should be good. When I teach the lecture, I use a textbook, and it's got a whole chapter on lab techniques that we cover. Okay. Let's see. Not for lab, but we do for class. Yeah. So check that. What you've got for lecture might have some good information for lab. What I've done is taken information from another not even another, from open resources, and put them into the what appears to be the first lab. It's really just background information. Okay, so let's look at balances. Let me just give you some highlights, and we'll go from there. Because with once we get going in lab, I'm not the kind of teacher that yells instructions in the middle. I just let you work. And if I see something go wrong, I let you know. And if you have a question, you can always ask me. Okay. So balances, 1, always use protection. Okay. Have you heard that before? Maybe mama, did mama tell you always use protection? Well, Dr. Jeff says, on my balances, on my $20,000 balances, always use protection. So let's say we might use a weigh boat. A weigh dish. Or weigh paper. So there's more than one lab that uses the classroom we'll have lab in. So there's 2 types of weigh paper. This is the real weigh paper, and then there's going to be little scraps of white paper. Don't ever use those because they're too fuzzy on both sides. So weigh paper is usually your best because it's a low weight material, and it's like a car, shiny side up. Shiny side up. Just like if you got to drive home today, try to keep your car like weight paper. Okay, so weight paper, I don't have a piece to show you, and it's hard to see, but you can feel it. One side's shiny and one side's fuzzy on purpose. So the fuzz on the bottom is to neutralize static charge. As you slide the paper onto the balance, you're going to rub off some electrons from the whatever that material is, a weigh boat, weigh dish, or weigh paper. Those little fuzzes on that weigh paper are to put the electrons back on the metal pan. So weigh paper's real handy. You can pre-shape it. I fold it in half, but you don't want to handle it a bunch. because the latex gloves do allow water to, your hands still get sweaty, but water comes through. You don't want a little bit of water on there. It will evaporate pretty quick, but it might not all evaporate. So don't handle your whey protection too much before you start your whey. Okay. Then let's go to a whey dish is an aluminum dish. Okay. I said whey paper is probably your best bet because it's a low mass. And so most of the mass on the balanced pan is your material. Well, aluminum dish isn't much either. So I like that bad boy right there too. And the aluminum dish, I put a little pour spout before. It's a round dish, so it's a little hard for me to pour out of it. So I'll shape it to a pour spout, and then I'll use water, DI water, to transfer the material into the flask. The aluminum whey dishes are usually people's favorite thing to use, or whey paper, depends on the size of your sample. These the whey boats are polystyrenes. Polystyrenes are chain link polymers. And so at the end of each chain link polymer, there's going to be a charge. And so they tend to be staticky, and I don't like them at all. If you want to use them, you can. A lot of people use them, but like the KHP has a little bit of static, and I go to dump it in the polystyrene boat, and some of it jumps out. Okay, so to take what you get. So it will say, this is the way we word stuff in the lab manual. W way out. 1.2 grams approximately exactly. Okay, so what we're trying to tell you, English language is all messed up, right? We want you to weigh about 1.2 grams, but record whatever it is, 1.2147 grams is checkaroony. Okay. If I look in your book and you got 1.2000 grams, it better be your lucky day. So it's a huge waste of time to try to get these things to exact masses. Instead, just go, and it helps you a little be honest when you're doing your titrations. If everything was 1.20000 grams, you'd sort of be biasing after your first titration. Oh, I know where it changes, so I'm going to try to get that again. But when you mix them up, like one is, so that's a no, and that's a 1.1014. That's a yes. So it doesn't have to be right at too close to even. Usually about plus or minus 5% is what you're trying to get here. Okay. All right, we talked about titrations already. All I wanted to talk about titrations, and the first day we won't make it there, but maybe on a week from Friday we will try a half drop addition. Okay, so the idea of adding half or quarter drops is that we get more accuracy. But another way, but it takes time, and always wash it down. So you think you're done, you're ready to try a half drop. But whenever you get close to your end point, oh, I can't drop. How would it? That's my wash bottle. Right, the little wash bottle. Always rinse down the burette tip, and the Erlenmeyer flask walls before you think you're close to the end point. Let's say it looks beautiful. Oh, it's beautiful. Add some water down the side. See if that's the truth. You're not don't try to impress anyone with how good it looks. You want the truth. It might look real good, but there's some drops that like stuck to the side from the stir bar. Rinse those babies down and see what's really in there. So always rinse near the end. We'll come up with some more goodies as we progress. We'll get better. The students that in the past have worked real hard on this first lab, and then they go, you know, that's my worst lab. I want to try to improve it. They'll do the entire lab in like 2 hours and get 10 points better than they were at the start of the semester. So you're gonna, just like an athlete, you're gonna get better with practice. Okay, and then so the last thing I want to do is warn you, okay, not that I look normal now, but I'll look weird when you you see me, because I'm going to be all bundled up. That's the way I teach lab. I always have worn gloves and lab coat, and now I'll have either a face mask, goggles, a respirator, and or a helmet. So you're going to be like, what? Yeah, I'm pretty afraid of bringing home the virus to my wife. So I apologize. I'm harder to talk to because of it, but don't let that, it's the same guy in the, so what do I wear? It depends what we're doing. If I have a face mask, that's probably what I'll have on Friday. That's not a splash proof deal. So whenever we're doing digestions or where I'm afraid you're going to shoot base in my face because of an accident, then I wear my splash proof helmet face mask. Okay. And I get too hot because I wear a face mask. So I wear a little respirator, and the respirator just pumps more filtered air into the face mask. Otherwise, I just steam up. So I apologize that I'll look weird, but to be honest, I kind of like looking weird. You know, I go down to this chairman's office and ask for something. He feels so bad for me dressed like that. He usually gives it to me. You know, I got a new laptop on order. Yeah, because I'm like, you know, I can't see the laptop when I got my face shield on. He's like, oh, go ask Cozy, see if they can get you, you know, accommodate you. And then sure enough, they did. So that's my last subject. It's 3:45. It's been long. It's been a long haul. Pat yourself on the back. I want to open the floor to questions. Let me get to, so I can see. You excited? I don't know. Don't answer that right now. But I will see you in person, live and in person, from behind a face shield with a respirator. And when you come in to lab, there's not going to be a lot of instruction. It's going to be, you'll find any available lab bench or drawer will have a combination to the locks in front of it. So when we come in on Friday, come in and pick out your spot. You know, some people like to be close to the hoods because we work a lot in the hoods. Those are prime locations. Some people like to be in the middle where it's not so quiet. The hoods are usually real kind of roar. During Quant Lab, we usually instigate the high flux for the hoods to try to keep a clean atmosphere in there. But or maybe you want to come in with your buddy and, you know, get benches close to each other. There's 4 big benches, and we're going to have 3 per bench, 2 on one side, 1 on the other. Then the next bench goes 2. That's our social distance arrangement. And then all reagents are on the back bench. You'll find that you need. And there's lines and paw prints for 6. Oh, I almost made the critical science there. 2-meter paw prints all around it. Up front is my desk, and we have a plexiglass shield in front of that, so you can come up and ask questions, but you're still to maintain your 2-meter distance. So it's a little bit like a grocery store in there. The balances that you are to use will be uncovered. There's all kinds of balances in there, and unfortunately we bought some that are low quality but look very similar to the ones we use. So only use balances that I've uncovered, and I try to warm them up for you right when we come in. I get them warmed up, and I think that's enough. That's enough warnings. Let's just, it's not, anticipation's always worse than reality. So don't worry about this stuff. Have a good 2 days until lab, and I'll see you there. Oh, if you're smart, you'll bring your own goggles. Last bit of advice is the best bit. Bring your own. I'll have the community ones, but I think they call it community spread for a reason, right? So bring your own goggles. If you don't have them, the bookstore and Fred Meyer and Walmart all have goggles. So good places to go. Questions? Silence is golden. I'll stay on for a few minutes, but we're all done. So thank you very much for your attention. I really do appreciate it. I'll see you Friday. Have a good one. Thank you. Take it easy.